Okay, so we are going to be practicing the improper integrals in this section. We want to find the following integrals if they are finite. I want you to recall that these are called improper integrals as we have seen in the last lecture, because one of the limits is an infinite here, or both of them are infinite, and so these are called improper integrals of type 1. So let's see, we want to find those integrals. How would you evaluate them? For example, integral from 1 to infinity 1 over x squared dx. As I told you, we are going to fix a t here, and we are going to call it a of t, this region. Actually, we are interested in all of this region area. We want to know whether the area is finite or not. But since it's difficult to consider it all, we just fix a t, and we just find this integral from 1 to t1 over x squared dx. We just calculate it. This is a power rule. We calculate it and we find it 1 minus 1 over t. And then we say, we just take the limit as t goes to infinity of that a of t. And if you take the limit of a of t, you get 1. So this tells us that this integral, this area is finite, actually 1, even if it looks infinite region. Okay? This is our key. A of t is this a to t f of x dx, or b of t t to b f of x dx. These are keys for us to get a result. So if a of t exists for all t greater or equal to a, then integral a to infinity f of x dx is limit of the a of t. Of course, provided that the limit exists. If b of t exists for all t less than or equal to b, then negative infinity to b f of x dx is equal to limit t goes to negative infinity b of t, provided that the limit exists. If we have both of them, both sides, we will do in actually 3. If both a to infinity f of x and negative infinity to a f of x dx are convergent, I'm sorry, just a sec. We note that we call it convergent if the integral is finite, otherwise we call it divergent, as I said before. But sometimes we may have like mixture of the two, like what we may have both infinities on both ends. We separate it into two. If both of them are convergent, then we are going to say that this is convergent, otherwise it's divergent. Let's look at this integral. 1 to infinity 1 over x dx. Is this convergent, divergent? If it is convergent, find the value. We form our a of t, 1 to t1 over x dx. The integral is natural log absolute value of x 1 to t, ln t minus 0, ln 1, a of t is ln t. Let's take the limit t goes to infinity. When t goes to infinity, ln t is what? Let's get the ln t function. As t goes to infinity, it's infinite. So this integral is divergent, actually. This I is the divergent integral. Let's look at this function, this integral. It's negative infinity to 0. Is it convergent, divergent? If convergent, find the value. We have to use the integration by parts. We have x e to the x dx. X is f of x, e to the x dx is g of x dx. U times v minus v du, we are going to apply. U is x, du dx is e to the x dx is dv. V is e to the x. Integration by parts works here. At the end, b of x, b of t is going to give us this expression. Let's take the limit as t goes to negative infinity. As t goes to negative infinity, this is going to go to 0, because e to the negative t down here gets very large, quicker than the numerator, so this is going to go to 0, and the answer is negative 1. And here's how we do it, actually. This is how we do that. So 0 times negative infinity, this is not good, so we separate it like that. This goes to negative infinity, this goes to infinity. We apply L'Hopital's rule, 1 over negative e to negative t, but this is going to go to infinity, so the result is 0. So this is an application of the L'Hopital's rule as well. So this integral I becomes negative 1. I is convergent, and the value is negative 1. Example 3 is we have improperness on both ends. 1 over 1 plus x squared. Is it divergent, convergent? If convergent, find the value. We separate it into 2 from 0. You can say a or 0, doesn't matter. Okay, first of all, 1 over 1 plus x squared is an even function. By symmetry, we can only consider half of it. So we can just look at k from 0 to infinity. Whatever we found, we have to multiply by 2 because of the evenness. And then we form our a of t, 0 to t, 1 over 1 plus x squared. Remember, integral 1 over a squared plus x squared dx is equal to 1 over a arctangent x over a plus c. We use that. Arctangent x, 0 to t, arctangent t minus arctangent 0. Tangent 0 is 0, so this is 0. Okay. What is limit t goes to infinity for arctangent t? Okay, we have to remember arctangent t. Arctangent t is t goes to infinity is pi over 2 as in the picture. We have to remember the graph. So I is equal to j plus k. J and k, both of them are pi over 2. 2 times pi over 2 pi is the answer. For what values of p the integral is finite, convergent, 1 to infinity 1 over x to the p dx. For p is equal to 1, we showed that this is divergent. We showed it before. Pi is not 1. What happens, we are going to form our a of t. A of t is 1 to t, 1 over x to the p. This is power rule. We apply the power rule. We get such an expression. T to the 1 minus p, 1 minus p minus 1 over 1 minus p. Let's let t goes to infinity. Then p is bigger than 1. Okay. If p is bigger than 1, then this is going to go to 0. P is bigger than 1 means this is negative 1 over infinite down here. So the answer is 1 over 1 minus p. If p is less than 1, then this is definitely infinite, so the result is infinite. So it's going to be convergent when p is strictly greater than 1. So we conclude that the integral I 1 to infinity 1 over x to the p dx is going to be convergent when p is greater than 1. It is divergent otherwise, and the value is 1 over 1 p minus 1. Next, we want to talk about integrals of type 2, improper integrals of type 2. We call them discontinuous integrals, integrands. Find the following integrals convergent or divergent. I want you to look at first the integrand, and the integrand is discontinuous at 2. Okay, so the domain is a half open interval, 2 to 5, 2 is not included, and f is discontinuous there. And similarly, secant x, which is 1 over cosine pi over 2 is 0, so pi over 2 is a discontinuity point. And then 1 here is a discontinuity point. So the domain is just a 0 to 1, 1 to 3, 1 is not included. And natural log of x is not continuous at 0. Okay? So we have that discontinuities here. Therefore, they are called improper integrals of type 2. If f of x is continuous on an open, half open interval and discontinuous on one point at b, then this integral is going to be the limit t approaches to b from the left a of t. I mentioned this before in my first talk. If f is continuous on half open interval, a is not included. F is discontinuous on a, then integral a to b f of x dx is limit t goes to a plus b of t, a from the right, provided that the limit exists. Okay, if this integral is convergent, this integral is convergent if the limit exists, is finite. It is divergent otherwise. We may have discontinuity point in the interval, then we are going to separate it into two pieces and handle this two separately. So we are going to say this is convergent if both of them are convergent, otherwise that it's divergent. Okay, So here's one question. 2 to 5, 2 is a bad point here. So we are going to form our a of t or b of t. b of t is t to 5 1 over square root of x minus 2. We do the substitution. U is equal to x minus 2. du is dx, substitution box. And then b of t is going to be 1 over square root of u, because u is x minus 2. And this is the power rule. We apply the power rule. We get 2 square root of u. And then we convert it to x, and then we apply t and 5. 2 times square root of 5 minus 2, which is square root of 3, minus 2 times square root of t minus 1. Next, we let t goes to 2. This makes sense. This is 1. 2 times 1 is 2. The answer is 2 square root of, let's see, t approaches to 2 or 1? Just a sec. T approaches to 2, by the way. Yeah. Let's go down here. 2 minus 1 is 1. 2 times 1 is 2. So the answer should be actually 2 square root of 3 minus 1. There's a typo here. So it's a finite number, so I is convergent, fine. There's another example. Secant x, which is the same as 1 over cosine. We have a problem at pi over 2. We form our a of t. 0 to t is secant x dx. Secant x has antiderivative natural log secant x plus tangent x, 0 to t. Natural log, we put it in. ln1 is, yeah. Then we put 0, we got ln1, so it is 0. A of t is ln, absolute value of secant t plus tangent t. Let's let t goes to pi over 2. T goes to pi over 2 a of t from the right. Secant t is 1 over cosine t. Cosine t 0, it becomes 0 actually. Okay, we approach from the left. Look, we rewrite it as 1 over cosine, sine over cosine, natural log. Natural log of the ratio is the differences of the natural logs. Natural log of 1 plus sine minus natural log of cosine. Cosine as t goes to pi over 2, this is 0. Natural log of 0 from the right is plus infinity. Actually, it should be minus infinity, and minus minus it makes plus infinity. Okay. And t approaches to pi over 2, this is 1. This is natural log of 2. Yeah, it just says we use that. And plus infinity plus natural log of 2, it's infinite, so this is a divergent integral. So the area underneath is a lot, it's big, very big. And here, example 3, there's a problem at 1 in between in this interval, so we separate it into 2, 0 to 1, 1 to 3, we call them j and k. Separately, we deal with them separately. J, 0 to 1, dx over x minus 1. We form our a of t. T approaches to 1 from the left. We look at this a of t. This is natural log of x minus 1. We put t and 0. Natural log of t minus 1 minus, if you put 0, it's 1. Natural log of 1 is 0. Natural log of absolute value of t minus 1 as t goes to 1 from the left. Okay. And numbers, yeah, this is like a 0. Natural log of 0 is infinite, negative infinite. This is divergent. So one of them is divergent, so we don't care about k, so it is divergent. And fourth example, 0 to 1 ln x. ln x has this shape, and it has discontinuity at 0. So what do? We look at a of t. As t goes to 0 from the right, a of t. We integrate that. We use integration by parts. We did this before with ln x. Use ln x, d use 1 over x dx. dx is dv, x is v. Integration by parts boxes. U times v and v times du. We get ln 1, 1, this is 0 minus ln t, t. t times ln t minus integral is 1 x, and we evaluate it from t to 1, we get 1 minus t. Let's look at it here again. b of t becomes t times ln t, minus t minus 1 minus t times ln t if I put this first. Okay, and what's the limit as t goes to 0 from the right? b of t, this is 0 times ln t, but ln 0 goes to infinity, so this is like 0 times infinite. There's a problem here, so we need to find the limit. So I'm going to take that limit here, limit t goes to 0 from the right, t times ln t. How can I find it? So I have to separate it into two, I have to write it as a ratio, natural log of t over 1 over t. As t goes to infinity from the right, this is negative infinite, this is plus infinite. So we can apply L'Hopital's rule. Let's apply L'Hopital's rule. The derivative of natural log of t 1 over t, the derivative of this is negative 1 over t squared, and negative t on top, and this is going to go to 0 actually, look at that. So the I is going to be, this is going to go to 0, negative 1, this is going to go to 0, and the answer is negative 1. So it is finite, it's convergent.